Today, we're going to uncover a really powerful way to find relationships in our chaotic world of information. We're talking about building family trees, but not for people. We're building them for data. This is all about hierarchical clustering.
So take a look at this. At first glance, what do you see? Maybe a piece of modern art, or, I don't know, a weird frost pattern on a window? It's beautiful, right? It's complex, it looks almost alive. But what we're actually looking at is a map of gene expression data. It's a scientific tool that takes a messy, overwhelming amount of information and turns it into a picture that we can actually understand.
And let's be real, we need tools like this more than ever. We are absolutely drowning in data. I mean, think about it. From the human genome to the millions of keywords people type into search engines every day. Our ability to collect information has just completely blown past our ability to make sense of it all. It's too much for any one person to handle.
So to fight back against this data overload, we use a solution called clustering. Now, that sounds pretty technical, I know, but the basic idea is super simple. It's really just a fancy way of sorting. You take this massive, jumbled up pile of stuff, and you start grouping it so that similar things end up in the same pile. That's it.
Okay, so piles are great, but there's a problem. Just making piles tells you what's similar, but it doesn't tell you how similar those things are. And it definitely doesn't tell you how the different piles relate to each other. We need a smarter way, a method that shows us the deeper structure of it all.
And this slide really nails the difference. On the left, you've got simple clustering. Think of it like sorting laundry into separate piles, whites, darks, colors. They're sorted, but that's it. But on the right, that's hierarchical clustering. It builds a genuine family tree. It doesn't just show us that the groups are different, it shows us how they're related. It reveals the siblings, the cousins, the distant relatives hiding inside our data.
So how do we actually build one of these intricate family trees? Well, it's a surprisingly elegant process, really. It works step by step, building from the ground up.
The most popular method is called agglomerative, which is just a fancy word for building up. Imagine you dump a giant box of Legos on the floor. At first, every single brick is its own little cluster. Then the algorithm looks for the two bricks that are the most similar and, click, it snaps them together. Then it does it again. It finds the next closest pair and, click, merges them. And it just keeps repeating this, over and over, until every last brick is connected into one giant structure. And the beautiful visual you get at the end of this whole process, that family tree, it has a special name, a dendrogram. This diagram is the master key. It's not just a pretty picture, it's a detailed map that shows you the entire history of how things got connected, from all the individual pieces all the way up to the single giant supercluster.
Okay, so we've got our map, but like any map, it's pretty useless if you don't know how to read it. And the secret to reading a dendrogram isn't just looking at the branches, it's all about their height.
Here's the key. The height of the horizontal lines tells you everything. A short connection way down at the bottom, that means those two items are super similar. But a big, long vertical line before two things merge, that tells you the two groups being joined are actually pretty different from each other. Simply put, height equals distance.
And this is where the practical magic of a dendrogram really shines. See, it doesn't just give you one final answer. Instead, you get to decide how many clusters you want just by cutting the tree. Imagine you're drawing a horizontal line right across this diagram. Every single branch that your line crosses becomes its own separate cluster.
Let's make this real. If we draw our line right here, see how it cuts through 4 of the vertical branches? And just like that, we've defined 4 distinct clusters. Pretty cool, right? And if you move that line lower, you'd get more, smaller groups. If you move it higher, you'd get fewer, bigger ones. The power is in your hands to pick the level of detail that makes sense for you.
Now here's a really crucial point. Why you can get that big picture view from up high. The dendrogram's greatest strength is actually down at the bottom. Those first merges that happen lowest on the chart, those represent the tightest, most reliable, most rock-solid groupings. That's where you can be really confident that those items are practically identical.
So this is not just some abstract theoretical exercise. Let's take a look at how these data family trees are solving massive problems out there in the real world.
Honestly, its applications are everywhere. In genetics, it helps scientists find their way through the massive human genome, grouping genes that act together, which could point to cures for diseases. In marketing, it helps companies find their tribes of customers who have similar buying habits. And in online advertising, well, it's absolutely essential for taming the pure chaos of millions of search terms.
Let's stick with that online ad example for a second, because it's a great one.
Researchers at Microsoft had this problem. The old way of clustering, which you see on the left, created these really rigid binary trees. Look at how similar phrases like Indiana cheap car insurance and Missouri cheap car insurance end up on totally different branches. It just feels wrong. Their solution, using a better hierarchical method, gives you the tree on the right. See how all those related phrases are now grouped together intuitively? Ah, so much better.
And this new approach wasn't just smarter, it was blazingly fast. This new method could build a complex family tree from 1 million keywords in under an hour. That is a massive leap forward, and it makes this kind of deep analysis practical on a huge, huge scale.
Now, of course, hierarchical clustering isn't the only tool for the job. Other methods like k-means are often faster, but they have one really big catch. You have to decide how many clusters you're looking for before you even start. But the unique power of hierarchical clustering, its superpower really, is the visualization. Other methods might just give you a number, but the dendrogram lets you see the structure, and exploring that map is often way more valuable than just being told where to go.
And that brings us to a final thought. We now have this incredible tool to map the hidden family tree inside almost any set of data you can imagine, from genes to language to how people shop. So the question isn't really if we can find the structure anymore. The real question is, what profound new relationships, what unseen patterns are just sitting out there waiting for us to finally discover them?